Thank you, Alex, for the introduction. So yes, I will talk a lot about robotics and quality diversity, evolution, reinforcement learning today. And you will see from time to time some names that are probably familiar with you and some instant logos for some of the works that we did together. The reason, my motivation behind my work with my lab is that I believe that robot has a tremendous potential for our society. So a lot of applications where we can already replace human in the most dangerous tasks they have to perform. We are still risking the life of thousands of people after a natural catastrophe, like an earthquake. We are still risking the life of thousands of people in order to mine, precious minerals with smartphones and laptops. All of this can be avoided if we can instead just send a few robots and so on. Obviously, I'm far from being the only one on the planet to do this, so that's actually a DARPA competition that took place just a few months after the catastrophe of Fukushima. That was a DARPA that actually put $1 million on the table and tried to bring the best mind around the planet to say, let's try to create a challenge where we train complex robots to drive cars, open doors, drill holes, shut off valves, and so on. And here you can just see that even if it takes the brightest engineers and researchers of the planet, there are always things that go wrong. You cannot anticipate everything that will happen when you deploy complex systems in complex environments. And so I like starting my presentation with this video because it's always quite funny and so on. But what is quite sad, the bitter truth behind this is that the 4 robots you can see on the side here are actual examples of robots that were sent into actual search and rescue mission and had to stop their operation after a ridiculous amount of time. For instance, I like the first example that was like almost 20 years ago, where they sent a robot after a mudslide in La Conchita. The robot had to explore a house to see if there was some people stuck inside the place. And the robot had to stop its operation after only 2 minutes. The reason is that the robot tried to do something extremely risky and dangerous. The robot tried to cross the living room. And so actually what happened is that the living room had a carpet with long hairs. The long hair got stuck in the track, and so eventually they had to send humans to save the robot that was supposed to save the humans. So here we have a situation where we cannot anticipate everything. And so my goal and the research of my lab is that we don't care if the robot falls. We don't care if the robot is stuck or something. What we want instead is the robot to be able to go back on its speed and continue its mission even after being damaged. And so for this, we are designing a learning algorithm to make robots more resilient and versatile. And so for this, for instance, that's an experiment, a paper that we published a couple of years ago and made the cover of Nature. We have this example robot. It's a very simple robot. It has 18 degrees of freedom, so 3 degrees of freedom of 3 motors per legs. It has a single sensor, which is this 3D camera that gives the robot information about its working speed, and that's pretty much it. There is no sophisticated sensor to perform diagnosis and things like this. It's just a robot, moving with its motors and seeing how fast it goes. And the goal, the mission of this robot is just to go straight forward as fast as possible. And here you can see the robot is intact, everything goes well, and the performance of the robot provided by the trajectory from the embedded sensors is 25 centimeters per second. All good. And obviously, given that I'm a very mean scientist, what I did is that I actually unplugged one of the cables that is at the very root of the leg. And because all the motors are connected in series, this means that just removing this cable just power off the entire leg. And this way sounds a little bit like an artificial scenario system, but it's not. Because, for instance, when you send rovers on Mars and so on, putting straps, putting covers and everything is actually quite expensive in terms of the weight that you need to carry up to Mars. And so when you send Mars rovers, you will see actually a lot of cable dangling like this. And this connection is kind of the big concern they have, for instance, at Airbus when they design the rovers. And you can see that this very simple situation, just a cable that is slightly disconnected, you can see that now the performance of the robot has been dramatically affected. And so here in this Nature paper, we proposed a way to do the intelligent trial and error. It's literally reinforcement learning, where here the robot is trying one new gate, it's observing its velocity, and based on the velocity, we'll decide what to try next. And just by this intelligent trial and error and reinforcement learning, it's testing and trying and selecting different behavior each time. Here you can see that the performance of the robot is already improving. The robot now finds something even better, and it will continue to explore because something even better may exist as well. But here, apparently, it's not the case. And so after that, we have some internal models that predict what are the likelihood to find something even better and eventually automatically stop. And so here you can see that after only 40 seconds of real-time adaptation, because here everything runs directly on the embedded computer, which was 7 years ago. So definitely your smartphone in your pocket is 10 times faster than this one now. The only thing... I'm infinity. Yeah. No, here. Can do. And so the only thing that is happening between the different shot is me taking the robot from the right to the camera to the left, and that's it. Everything else is running on board and in real time. And what is very interesting is that this slow motion reveals that the gates are actually very dynamical. So you can see that now the robot is actually pushing or using its back legs to push itself forward and avoiding using the middle legs. And this kind of dynamical behavior is usually quite hard to obtain with gradient descent, because actually the fitness landscapes or the reward landscapes that you try to optimize is actually very rugged, and finding a proper gradient here is usually quite challenging. But the big question you may be wondering is, how can we actually learn this kind of sophisticated behavior on board in less than 40 seconds? Well, the answer is that we don't learn a lot of things in real time on the real system. What we do instead is that we try to generate, prior to deployment, a huge amount of prior knowledge, a huge amount of different skills, and then when there is a situation that requires adaptation, we then quickly leap through all this prior knowledge, try to find one that is still relevant now. So here, when I was presenting the adaptation, I was saying that the robot tries different behavior, not that the robot was trying different actions. So in a sense, we were doing reinforcement learning not at the action or parameter level, but more at the behavior. And so here the question was, okay, how can we try to distill all the different skills, all the different behaviors that our robots have, and then use this kind of collection of behaviors and skills in order to adapt? So for this, we use quality diversity to try to find, single learning process, all the different behaviors. That's exactly what I just said. And so for that, quality diversity, for people who don't know, is an optimization algorithm that aims at finding a collection of very diverse and high-performing solutions. And so that's very good. For instance, for a legged robot, you can try to find all the different ways that the robot can use its leg to go forward by using its leg differently. And so this is, for instance, exactly what we have here. Here are just 9 examples of gates that are using all the 6 legs a little bit differently, all of them going straight forward as fast as possible. And here you have actually the grid that we obtain with Maply that I will mention in a few minutes, where here every single pixel of this matrix is actually a different working gate. And the color corresponds to the working speed, and the more red is the color, the faster it goes over. So here you can see for a lot of different working gates, each one of them being high performing. In number, we actually found more than 13,000 different ways to work. And what is quite interesting is that some of the gates are actually very creative. So for instance here, my simulation tells me that the legs that are circled in red are in contact with the ground less than 30% of the time. Less than 10% of the time. It's almost never in contact with the ground. At the first time I saw this example, I was kind of puzzled, because this robot is not supposed to be able to fly, so how can it work before touching the ground? Well, Maply or quality diversity just found worked well. He just tripped on his back and walked on his knees, because I was just detecting the contact with the tip of the legs. So here is the first example of how quality diversity, by its search for diversity of solution, finds very creative ways to solve problems. So quality diversity, for some of you who don't know how it works, the idea, it's an optimization algorithm. It can be also seen as a reinforcement learning algorithm, where the goal is, for instance, to optimize a fitness function, which here in this case can be, very traditionally in the gym environment, the forward speed minus the energy consumption. Okay, but one key difference with quality diversity is that we also have a descriptor or feature function that characterizes the type of solution that we are observing. So here, for instance, for a legged robot, we can say that the type of solution we are looking for are solutions that are using or touching the ground with different proportion of time with each legs. So for instance, here, given that we have a worker with 2 legs, we can define a descriptor space that is a 2-dimensional vector space, where each dimension corresponds to the proportion of time that each leg is in contact with. And so typically, what we are looking for is to think this kind of collision, where we will find different solutions across this descriptor space. So, here you will spend most of your time in contact with the ground with the foot 1, and here most of the time with the 2. Here you are literally flying, so that's why we don't find anything. Here you're always riding both feet and so on. And what we want for each of those cells, we want to find one solution, but we want to find the best one, so the most yellow one as possible. And so, for instance, as I said, here we'll have a solution that will use the legs 40% of the time on both legs. Here, it will be one that will drag with one leg. You have the opposite with the other leg here, and you can also drag with both feet if you can. And so the goal is really to cover the space of possible solution. So all the algorithm works. So here I'm introducing Mapedit, which is a very standard algorithm, very, very well established. Also extremely simple to implement, something like 5 lines of code, but it's actually very effective. It's not the fastest one, but usually give it more compute, more time, and it converges systematically to very good results. And so you initialize this kind of grid, just a table with all your solutions are run according to the view of the descriptor space. You initially just generate some random solution, you evaluate them, and you store them in the grid according to the descriptor and fitness. And then you just repeat this rule. First, you randomly select one of the solutions from the grid. Then you apply some mutation, like a genetic algorithm variation, some mutation crossover, whatever you like. You evaluate the solution. So here you will get a new fitness and a new behavior descriptor. And then you add the solution back to the archive. So to add the solution back to the archive, you use the descriptor to know into which cell it goes. And so, for instance, if it lands somewhere here where there are no solutions, you just add this solution to the cell. That's very good. This means that you discovered one more solution for your code. Conversely, if it lands somewhere there is already a solution, here it's simple again. You just keep the best solution out of the two. So if the new solution is actually better, then you just replace the old one by the new one. And that's again a good news, because this means that you improve the quality of the solution contained in your collection. I talked about the descriptor. For instance, we were using the contact with the ground and so on. But sometimes in certain tasks, we don't know what can be a good descriptor. So here we can use actually unsupervised learning, like a VAE or a transformer, in order to encode automatically, the type of information we can collect on the agents, like its trajectory or the trace of all its states, into a latent representation that can serve as a behavioral descriptor. And that is quite interesting because, in a sense, a VAE or an autoencoder tries to capture into a restricted embedded space or latent space all the entropy of your data sets. So this means that then if you use this latent space as a behavioral descriptor and you try to maximize this means that in practice you are trying to maximize the entropy of the behavior or the solutions that you can observe. And so, for instance, here, what we did is that we took the trace of all the states, like the orientation and position of the robots during the entire episode. We fed this into a latent space, and we used this in order to learn the descriptor. And what we found is, well, surprise, the algorithm discovered how to work in every direction without having us to define this. But not only, it also found that the robot can just stand up, because that's, again, quite different from working in every direction on the planar ground. And if you are already tired with working robots, I can also... Okay, you are missing the good part. Let me try again. You can also roll if ever that's interesting. Again, that was discovered by Aurora, this algorithm that combined unsupervised learning and quality diversity, without any prior insight from engineers. But we didn't know that this kind of solution existed before we discovered it in the algorithm, in the results. But if you're familiar with neuroevolution, you know that it's not super data efficient. On the other hand, you have different reinforcement learning that is way more data efficient. So can we try to combine both of them? Well, the answer is yes. When I described quality on Mapedit, I showed you that you can modify the solution by applying some genetic algorithm, mutation, and crossover. But you can also just follow gradient. So what we do with this algorithm is that we follow the same selection, mutation, evaluation, addition loop as Mapedit, except that every evaluation we do, we store all the transition in a replay buffer, we train an actor critic algorithm next to it, entirely TD-free, and we use a gradient from TD3 in order to perform mutation of our solution. So now we have half of the solution that we mutate that follows a normal mutation from mapillary, and the other half that just follows the gradients from the actor critic. And what we observe here is that we can now scale quality diversity to large policies with more than 20. I think we made up to 100,000 parameters and solve any tasks that you usually encounter in deep reinforcement learning. So that's very good. For instance, here at the worker task with mapillary, you can see we can more or less cover all the ground by some tricks, but the performance is very high. As soon as you combine this with gradients, suddenly you will have the same coverage, which improves the performance by a lot. But there are some limitations. So for instance, here, when you have the ends and the fitness, so here we have a task where we have the ends and we want to have different policies that can lead the ends to different locations, moving forward, moving backward, and so on. And the fitness we want is to minimize the energy consumption. So that's relatively, so that's what I'm saying. Fitness is the energy, and descriptors is the final location of the robot at the end of the episode. So if we take a solution like this one that goes quite fast forward and roughly straight, that's good. But the issue is at the end, if we follow the gradients from TD3, for instance, that try to maximize the fitness, so try to minimize the energy, what we obtain is a new solution, but that will force the robot to not move, because moving will penalize the fitness. And so here we can see that following the gradient just limits our exploration capabilities. Just to let you know, so this is here the video, right? And you can see that the robot is just not moving because it followed perfectly the gradient. So here we need to find a solution, because while in some tasks that is not just minimizing the energy, PGA was working well, it's definitely not helping much as soon as you take into account things, when the fitness function and the exploration or the search for diversity are not perfectly aligned. So the way we approach this was with DCG mapillary, so descriptor condition gradient. Is the idea that we want to do exactly the same, but we want our actor critic to give us a different gradient depending on the descriptor of our solution. So if I have a solution that goes straightforward very, very fast, I want the gradient just to improve this solution while maintaining its capability to go quite far straightforward. If I have a solution that doesn't move, that stay on spot, I want, again, a different gradient that would just change the energy consumption. So here we have exactly the same algorithm as before. We collect the transition inner replay buffer. We compute a new actor critic, but this time the critic and the actor are both conditioned based on the descriptor of the solution that it's imitating, or by. And here you can see that this is the original mapillary. This is mapillary with gradient, and this is mapillary with gradient conditioned on the descriptor. And you can see that we can now cover the entire space. We can even reconcile a little bit the reward function and the diversity function that we are both optimizing. Another good thing is actually here, as I said, we are training from the transition observed while trying to generate this archive. We are training an actor critic here. This means that we need to train an actor critic in order to do the bootstrap and the Bellman equation when we train the critic. And so here we have an actor that's a policy that is now conditioned on the descriptors that have been observed here. And so this means that in practice, we are naturally distilling all the knowledge that is contained in this archive, which is composed of disparate policies, one policy per cell, into a single policy that is directly conditioned by the descriptor. So I will just stop here in terms of combining quality diversity with different force modeling, but we go way further. So we have a paper that got accepted last week called DCRL. So it's literally DCG mapping, but with even more tricks like actor injection and things like this. That works even better. We have also another way to do quality diversity, purely in the deep reinforcement learning setup. So without mutation and without discrete policies. And a couple of, last year we published with some people from USANIP a survey where we compared, the capabilities of quality diversity to serve in the domain of unsupervised reinforcement learning And what we observe here is that compared to the standard SMART, Diane, and DADS, quality diversity algorithms are excellent candidates for this kind of task. So here is a video, for instance, of what we achieve on the real quadruped robot following all those principles of finding a single policy that can exhibit a lot of different behaviors. And so here we have a single policy that can be conditioned on using only 3 out of the 4 legs, so any one of those. It can also have different type of frequency in terms of the gates. It can walk, in every direction. It's robust to different perturbation. It can change different types of gates, or it can also change the spacing between the legs. So here we have a lot of different kind of levers that we can play depending on the situation we want to face. Another thing that we discover is, in order to make quality diversity faster, you can either combine it with more smarter ways to do mutation, like different reinforcement learning, but you can also leverage hardware acceleration. So typically, we have been playing with Brax and JAX for a couple of years now, and the good thing is that we can actually run in parallel hundreds of thousands of environments and collect all those data very quickly. And so we were wondering, okay, can we use this in order to, instead of evaluating 10 solutions in parallel in a market loop, can we try to evaluate hundreds of thousands of solutions, and doing maybe instead of doing 1 million evaluation in 1,000, let's say, or in 10,000 generation, what if we do 1 million evaluation, but in 100 generation? What would be the impact for quality diversity algorithm? And what we observe is that actually quality diversity algorithm scales super well. The fact that it's actually trying to locally optimize a lot of different solutions that are all very different, more or less connected or related to each other, offers a natural substrate for this kind of massive parallelization. So for instance, here we try the same map-it algorithm, except that at every generation, we select batches of solutions that we evaluate in parallel, retake, and then add all of them in parallel. And we tried a batch size of 4,000 solutions, which is already quite a lot, up to 130,000 solutions. And what we observe is here, when you compare just in terms of the number of evaluation, it's literally the same thing. You don't see any difference. But in terms of runtime, you can see that here we have a significant speed. This means that if you just use faster GPU, your algorithm will go faster. To give you a sense of what this brings on the table, the experiments of the Nature papers that we used, in order to generate the type of solution was taking almost 10 years ago, 2 weeks running on a very good workstation just to generate the archive of 13,000 solutions. Now I can get exactly the same result in 4 minutes. So this means that now we can actually iterate way faster with quality diversity thanks to this kind of tool. And so looking at this, we just decided to work with you guys actually in order to develop a library called QDAX that implements most of the quality diversity standard algorithm and tools in JAX, leveraging this kind of massive parallelization and offering a good place to start using quality diversity, where like all those algorithms, most of them that I presented today, that are already implemented with notebooks that you can play with. Okay, so I was talking a lot about, optimizing one fitness function and so on, but there are a lot of engineering problems where you have more than one objective to optimize. And naturally, and that's actually where we started our collaboration with InstaDeep 2 years ago, or 3 years ago, was to actually improve map-it, but in order to be applicable to multi-objective problems. And here's the idea is relatively simple. It's literally the same algorithm, except that in every cell of the grid, instead of keeping one solution, we keep a Pareto full of solutions. And we simply change the addition mechanism. So we just keep the solutions that are non-dominated. This means that if you have a new solution that arrives that is dominated, you just discard it. But if a solution arrives and is non-dominated, or even better, if it's dominate solutions that are already in the cell, you just discard the solutions that are dominated and you repeat like this. And so that gives us eventually a collection of Pareto faults, each one of them covering the trade-off of the objectives, but still featuring the same features of the script. So for instance, we use this last year in order to discover a new crystal structure with different properties, but also maximizing at the same time the stability of the crystal structure, and some other properties. And what we observe is that with quality diversity, we can actually discover materials that are better than the materials that we know right now. Of course, in order to do this, we were using large models or large language models actually to estimate the performance of those crystal structures. And obviously, those models will hallucinate or be wrong. But that's not bad news. That's just good news. This means that we can use quality diversity in order to generate a lot of counterexamples where the model may be wrong, and that's good. We can just try to generate those materials in real life. We can try to collect some data about them, and then we can just use this new data in order to improve our model, and we can have this kind of always improving data sets and models of crystal structure. With Thomas, we also try to apply this, or we did apply this also to involve the structure of proteins, and we have a couple of papers on this. But, I already said that we can combine quality diversity and gradient. Well, we can also combine multi-objective quality diversity with gradient as well. So here we just follow exactly the same thing. Here we are just, instead of one gradient from one TD3 actor critic, we have actually two TD3 actor critics that provides one gradient for objective 1 and one gradient for objective 2. And here you can see the performance in blue. We are, by following this kind of dual gradient, we can go way better than any existing algorithm, considering multiple objective like in HGA2 or even the multi-objective mappings. But what is interesting is that sometimes you want, following one gradient or following the other is not equivalent as following gradients in between. So if you want to make progress in both objectives at the same time, you cannot just combine the two gradients together because they can be canceling each other. There might be some underlying effect. So here we wanted to find a way to kind of have a gradient that is not only pushing on one of the extremum of the Pareto form, but can also push in between in any directions that you want. And so for this, we actually use the same tricks than the Dissinger map, and it will just learn a single actor critic, but this time that is conditioned on the preference in terms of trade-off between the different objectives. So in a sense, it's conditioned on the direction of this blue arrow here. You just define this scalar, and it will give you the corresponding trade-off and try to push the gradient in this direction. And here again, we show a significant performance improvement here in this paper that is currently under review. But maybe a situation that you encounter quite a lot is that when you have environments or test cases that are uncertain, typically where the rewards, the fitness function or the descriptor function are noisy, uncertain, that becomes a big challenge because you can generate like thousands of different solutions that are all working well. So here's you have the expected behavior, but then when you apply, in practice, you realize that there is like the sim to real transfer gap that makes the robot actually deviate and collide and so on. Well, what you want is to make sure that the solution you have will always exhibit the right behavior. And if you play with Brax a little bit, you're definitely aware of this problem because Brax on GPU is absolutely stochastic. So when you train a policy on this robot, that it starts here and try to work somewhere, here is the trajectories of the same policy that was learned using MapEdit. And you can see that given the stochasticity of the environment, the same policy reevaluated multiple times and lead to a wide distribution of trajectories. So that's not very what we want. What we want is actually to have something way more robust, way more reproducible. And so we worked a lot on this, as here what I'm saying is, the first solution that you will think about is, well, when I evaluate my solution, I will just evaluate them 10 times and I will record the median and the standard deviation of the fitness and the descriptor and use this instead. That will help. Yes, it does, but it's not doing everything. What is quite important is very frequently to reassess your solution. Never let a solution in your archive for too long without being tested, because that might actually just prevent a better solution to take its place. Because sometimes you evaluate your solution once, it's very likely it has like a unrealistic, very high fitness, and that will just get stuck in the archive for the entire learning process. So just reevaluating all your archive from time to time is an excellent way to just encourage reproducibility, because only reproducible solution will stay in the archive generation after generation. And that helps. We have also some mechanism like deep grid where we store actually within each cell's multiple solution. This means that when we reevaluate one solution and it turns to be less effective than expected, we can just throw it away, and we have like the depth of the solution to give us alternatives and to never lose solution. The good thing is here we have an exact example of a situation where we care about more than one objective. You can have your primary objective and a secondary objective that is actually the reproducibility of your solution. So here we can use the algorithm that I just presented like 3 minutes ago, where we optimize those two objectives. And you can see that we started from this, and we end up into trajectories that are reproducible, and this one and this one. And in terms of performance, we maintain everything in terms of coverage and QD score over a wide variety of. One thing that I forgot to mention, it's quite important to correct your metrics when you use this kind of environments. What I mean by correcting the metrics is take your final archive and reevaluate every single solution 10 times, for instance, and then try to store them back in the archive to see what is the actual archive that you obtain at the end of your algorithm, and not what the archive thinks it found without being certain about the metrics and the value that it actually contains. And finally, how can we prevent the intractable growth of the archive? Because the issue is that if you want to do ever more complex skills, you will have an ever bigger and bigger archive, and that's start to become intractable. So here, what we proposed was to use hierarchical quality diversity. The idea is that you can use quality diversity, literally map it here, to control the robot to do some primitive tasks. Like here, we have this planar robotic arm, just a 2D robot that is just learning how to reach any point in its vicinity while minimizing the variance of its joints, because that's pretty smooth movement. So the good thing is that now that we learned how to reach any points, we can use this repertoire as our action space. And we can elevate the search in a more abstract way. So now we can learn how to connect the dots together in order to draw lines of different length and different direction. Now that we learn how to learn lines, we can learn how to connect the lines in order to form arcs and circles of different radius, length, and direction. And now that we learn how to do lines and arcs, we can learn how to try to reproduce MNIST. So here I use the MNIST dataset, embedding all of this into a 2D data space, and you can auto-encoder to automatically define the feature descriptors that I was looking for, and we use all the stack here to learn how to reproduce the MNIST dataset. The good thing here is that actually this was trained on this planar robotic arm, but the only layer of the hierarchy that actually interacted with the robot was the very first layer. This means that if I just learn the first layer for this humanoid robot, now I can transfer all the rest of the stack to this new layer, and now I have a humanoid robot that learns how to draw the digits, even if it never encountered an MNIST sample ever. We applied exactly the same thing on our example robot 2 years ago, where we first learned how to use one leg to move the legs in different directions, different speed, and so on. Then how can we connect those one leg movements over the 6 legs in order to just learn how to do one step? And then we learn how to connect the steps together in order to make a gate. And here you can see that we can use this in order to solve at the same time the damage recovery problem and a maze navigation task. So I don't know if you see it clearly here, but actually there's only 5 legs. One leg of the robot was completely ripped apart. There is, again, no sensor, no elements to diagnose the situation, but the robot is just learning how to adapt and finding in the hierarchy what remains viable given the situation. And another line of work in my lab is I'm showing you a couple of examples of the creativity behind quality diversity. And we wanted to see how far we can move with that. And so we tried this year to play with a linear environment, which is kind of an extended form of similar automata from the game of Earth and Conway, where here everything is continuous, is on multiple channels, so that we have RGB colors and so on. And instead of using discrete folds, it's actually using kernels in convolution in order to apply and to form this kind of feature. And here what we observed is that we can use the notion of unsupervised quality diversity, we will discover, a never-ending series of different species and diversity. And actually, those results, even if they were published 2 months ago or 1 month ago, we have even better results for it. Another line of research is following this kind of open-ended quest is, can we use quality diversity with LLMs, typically with ChatGPT, in order to produce code? And so here we actually combined LLMs with quality diversity in order to generate a never-ending collection of pipelette environments. Here we have actually an LLM that will give us a task, like you will see a couple of examples of prompts in the next slide, and then we use quality diversity to figure out if it's a task that is novel enough, interesting enough, and if yes, then we use an LLM to generate the environment, but not just the environment. It actually produces the Python code, so the definition in Python of the pipelet environment, the definition in Python of the reset function, of the state function, of the reward function, and you can let the algorithm just discover and play on its own, train directly the reinforcement learning agent, and then reflect on this if the environment is feasible or not, and use this in order to form a curriculum in this never-ending process of discovering new skill for agents. So for instance, here is a kind of collection that we found after running the algorithm. Every dot is a suggestion from the LLMs about an environment, and you have the different fonts or tasks that are provided, and you can see all they are connected together, forming a sort of complex curriculum of always increasing complexity. So for instance, you have like some very interesting one, like a busy restaurant table service, or you have like a clearing up a construction site. You have a lot of different things like kicking ball for moving gates on zone markets by moving targets and so on. All of this was fully discovered by collision diversity when combined with LLMs. And the interesting thing is that it's always kind of, moving from very simple tasks to more complex tasks. So forming also a curriculum for the reinforcement learning agents that we are learning, because the two are kind of learning together. And to finish this presentation, a couple of real-world applications. So this is what we did last December. We're working with a DARPA now on trying to make complex systems safer to drive, so typically to avoid scenarios like the evergreen container ships that blocked the Suez Canal a couple of years ago. That was actually a control theory problem. The issue was that there was a very strong lateral wind that was coming from this side, I think. And because of this wind, the pilot had to accelerate to make sure that the ship was still controllable. But the issue is, this is a kind of a narrow canal. The ship is quite big for this kind of canal. And by accelerating, it was actually increasing the Bernoulli effect, meaning that when the ship was getting closer to the coast, it was actually pulled towards the coast even. And if your ship is pulled towards the coast, as a pilot, what do? You steer the other way. And if you steer the other way, you get closer to the other coast, pulling you even more toward this edge. So that was just causing some oscillation and leading to this situation that we're on. So with DARPA, we worked on making a system that can kind of make this kind of external perturbation, like the wind, like the Bernoulli effect, completely transparent. And so here our playground is this kind of US Army robots on this large treadmill. And here we have a human that is still operating the robot, which uses a PS5 controller. And we are moving this robot along this treadmill. So the treadmill here represents the canal. And what we have in that you don't see is that there is kind of a man-in-the-middle attack that takes the information about the location of the robot with respect to the sides of the treadmill. And based on this, it's actually altering the behavior of the robot so that when the robot is very close to the edges, it's actually attracted to the edges even more to simulate the Bernoulli effect. And here you can see that proof of system, and also last thing, the yellow tape are just a fake obstacle just to force the pilots to not stay in the middle where there are no perturbation, but to execute some complex maneuver. And you can see that with our system on, the robot is relatively simple to drive, while without our system, the pilot has to fight against all the perturbation. And the way we are doing this is, again, exactly what I told you so far, is that we kind of captures this time in a continuous latent space all the different situations that can happen to a robot. And during deployment, we are very quickly trying to flip through everything we know, trying to find, okay, this is a situation that we know about these characteristics, so we can already plug and play our contingency measure. And here we are learning directly the effects, and, in real time, we are trying to very quickly understand and predict the effect of the bandwidth perturbation. When the situation is very, very strong, you can see that a human pilot just cannot do it on its own, and thanks to our system, we can recover. We also did the same thing with wind. So far here we have a static wind direction that is taking on the simulated sail. Again, the man-in-the-middle attack. And you can see that for our systems, the pilot can easily drive the robot around with almost no issue, while here the pilot has to always stop, reorient itself, and continue its course, making the task very difficult. I have the obligation to show you this slide. And yeah, just to finish, I want to thank all my fantastic collaborators. One of them is here in the room, working from time to time with you. And I hope that I managed to convey those messages that we can use creating diversity to generate a large collection of diverse and creative solutions, so that we can combine your evolution, creative diversity, with gradients to kind of bring the best of two worlds, so that we can use multi-objective quality diversity to fuel the discovery of new methods, new approaches, and new discovery in general, but also to promote robust solutions. The hierarchical combination of skills, VR quality diversity is also a nice way to complexify the behavior of robots. And finally, that quality diversity is a nice path for open-ended discovery as well. So now if you have any question, I will be delighted to answer this. Yes.
Yeah. When you were talking about the multi-objectives,
Mhm.
and you had the rotor run, and you had like a spectrum of different directions
Mhm.
you could sort of push. The thing I quite understood of it is that not just equivalent to basically specifying the weighting between the two objectives, that it's like a secret or it's like a standard protocol.
It is, but it's exactly this. But now we're actually training an actor critic that is aware of this weighting and can reflect or change its value function on the fly based on this specified weighting. And so that's exactly what we do. But then, because we have an actor critic, we can then backpropagate this to our policies as well.
Okay, so semi-relatedly, when you were talking about conditioning the quality diversity, which you're super familiar with, so I don't be saying something, but when you were conditioning the quality diversity, like the training and actual quality gradient on the descriptors, like how do you ensure that after you've updated the policy, like you still you still are like within the same descriptor slot as you were?
That's an excellent question. We don't. That's the first thing. We don't, but we want to make sure that the goal is by training the actor critics that way, just by so the way we do is that we label our transition based on the descriptor from the data that was, the trajectories that were used to collect the data. We have the final descriptors, and this is what we use in order to label our data or transition in the replay buffer. And then we just train the actor critic. But what happened is we have no guarantees that is not happening, because we just say, I want to follow a gradient that is matching the data that we observed. And if not, we just scale down the reward, so we penalize, the value function is kind of penalized if it's deviates from the intended descriptor.
Oh, so you do have to change the rule to kind of keep you, incentivize you to stay within the same descriptor slot.
So not directly in the reward function, but more in the bootstrap function or the Bellman equation. We have an additional weighting term here.
Okay, because I would have just thought that like otherwise the policy would sort of collapse to like the descriptor that's most useful for optimizing the actual reward.
Yeah. So indeed, so that's what we do. We say as soon as it starts to deviate, again, just from the transition in terms of descriptor, final descriptor, then we kind of scale down the reward. And that allows us to make sure that given a descriptor fed to the critic, only one trajectory or one behavior is optimal. And so the critic is just trying to give you what is the best action to do in order to execute this behavior that leads to the highest fitness or highest reward.
Okay.
So we don't have any guarantees that it will be the case, that the gradient will maintain the solution in the same BD or things like this. But in practice, we observe from experimentally that the applying the gradients maintain the solution in the same cell. Definitely way better than random noise or even PGA.
Mm-hmm. Okay, thank you.
So CRISPR's most of the setup is only it's more like are you trying to train in the real world directly? Would that be practical with the kind of method you're developing?
I can answer after the iClear deadline. So we are literally working on a paper of one of my students spending his time in the lab trying to directly learn on the quadrupeds directly without simulation, a gate that can do a lot of different things.
Cool. So maybe I can read. Oh, go ahead, and then I read Donald's question.
Yeah, I was just going to ask. So I'm not exactly sure how you're exploring the diversity space. Is it because is your gradient just coming from your quality metric? So is it like you don't care that you're always optimizing the fitness and that you're trying to just move around, but like, is it you're combining the descriptors in a way to try and move the diversity? Could you explain that a little bit more?
This is an excellent observation. Indeed, we never follow any gradient of diversity. In fact, there is one algorithm that was actually proposed by Thomas Pierrot during his PhD, where he was actually defining two gradients, one gradient of fitness or performance and one gradient of diversity. But this is kind of a challenging question because while we usually define the reward at the time step level, that we then accumulate in order to get the return at the episodic level, the descriptors is often defined at the episodic level. And so then if you want to use, TD3 or an actor critic algorithm, you will need to find the same representation of the reward at the time step level, but for descriptor. And so then if you can do this, then QDPG, which is the algorithm from Thomas, will definitely work very well for that. But in practice, we found that it's very difficult to find a description that works at the time step level. But what we observe is here, if you notice, we never completely get rid of the genetic variation. Every time we combined mapility with some gradients, we always leave a big part of our evaluation being mutated by just random Gaussian noise and so on. And so here, in a sense, that kind of just blur a little bit the performance, give us a different solution, and then naturally expand the diversity. On this note, so when we did this analysis, actually with Felix Chalumeau from study, we found something very interesting. Is you have when you run the mapility with TD3 algorithm together, you have three sources of new solution. You have the solutions that are produced by the genetic variation, so just mutation. You have the solutions that come from the actor critic, and you also have the actor itself. Let's just ignore the actor for the sake of simplicity. And so we were wondering, because we can see over time, generation after generation, where the solutions that have been added to the archive, either because they are novel or because they are higher performing, where do they come from? Do they come from the policy gradient? Do they come from the genetic variation? And what we observed, initially when I designed PGA mapility with my student, I was like, we will have the genetic variation that will just do the diversity side of things, and then we will have the gradient descent that will just poke down and make sure that we get for every cell the best solution. What we observe is exactly the opposite. What we observe is initially the policy gradient is the most useful because it just generates a lot of good solution, and then it starts to not perform or not do much, while actually the random variation then start to do very well. So that's still a phenomenon that we actually observed in multiple algorithms across multiple papers. So we are kind of certain that this exists, but we don't really know why. My own hypothesis is actually linked with the lottery ticket hypothesis. With this kind of big network, it's very, very difficult for genetic algorithm to do anything because it's just,
randomly mutating such a huge network is kind of a waste of time, while policy gradient, we know, thrive in these kind of environments and will actually direct the quality diversity in the interesting part of the search space. You have 20,000 parameters, but not the entire space is interesting, only a very subset. And so here we have the policy gradient that just take Maplet by the ends, bring it into the right location, and then the noise of Maplet does all the rest. And my intuition is, actor critic are good, but the issue is that they are actually an approximation of the value function that is then approximated by a suboptimal actor and so on. So it's kind of an approximation of an approximation. And eventually, following this kind of approximated gradient may be more misleading than just following no gradient and doing some random noise at the parameter level.
And second question, you mentioned that archive is non-stationary almost. Like, why is that when you've explored a bunch of new solutions, you go back to an older one, the performance has changed?
So it's not that the performance has changed. It's not non-stationary. It's just the environment is noisy. So every time you evaluate a solution, the fitness you will get will be different just because of noise. And the reason why I'm saying you need to reassess is because a solution may have been very lucky the first time you evaluated it, but maybe just kind of an illusion. It's not a very good solution. So you need to just put into question those questions all the time. Of course, if you're at the very, very beginning of your algorithm, most of your solutions are degenerated anyway. It's not worth actually trying to evaluate every solution one at a time, because anyway, you will discard them in 5 minutes. So that's why you have to take into account this kind of dynamics, that some things that have been good at some point may be just an illusion, or maybe actually very good, but you need to include, to improve your budget to reinforce your confidence in this performance and this kind of dynamics.
So it's just computationally cheaper. So
Absolutely.
instead of doing 10 tests every time, you just go back when you need to.
Exactly.
Okay. Cool.
Just curious about whether this year and the next, I guess, will be the years of robotics in AI. There's been LLMs that people are trying to plug into those robots. So there's Tesla, there's Figure AI, and so on. Do you know if any of this company has adopted quality diversity methods? And if not, why do you think so? Because you clearly made a compelling argument for it.
So what I know is actually Meta is using quality diversity to train Llama. It's actually used to make sure that it's not deviating from the safety prompt they have, or safety conditioning. So it's just using quality diversity to find either more sophisticated way to work around the safety by always trying to attack by prompt engineering. So it's already used in order to make QD better, LLMs better. I know that there are some companies, literally Sakana AI, using more and more quality diversity in order to make, either to leverage the creativity, a little bit like, so OmniEpic was done with Jeff Kloon. Jeff Kloon and Sakana also did the AI scientist, capable of generating by themselves. You can easily imagine that for an AI scientist, instead of generating just one hypothesis, you generate hundreds of hypotheses, and then you go through all of them would be definitely the way to go. What else? So there are a lot of things that are happening, but that are currently kind of in stealth mode.
Any other question?
Yeah.
I'm sorry. Thank you. Is there a magnitude increase in the kind of compute that we need when we're trying to basically, let's say we have some sort of a robot. I basically just learn a handful of behavior patterns. It's probably not going to be sufficient for any possible case, right? But what's the trade-off in terms of like learning such a huge sample space versus just trying to learn a bunch? And in most cases, you're probably not going to encounter other stuff. Just in terms of, I guess, how easy it is to set these things up.
This is an excellent question. So for instance, here, that's a good analysis, because here, instead of limiting the algorithm to the same number of evaluation, we actually limited the algorithm to the same wall clock time. And what happens is with Maplet, that is very, very simple. Again, selection, mutation, evaluation, addition, we were able to do I think 1 or 2 order of magnitude more evaluation than with dyades of deep reinforcement learning. One thing that we observe is that actually now we can run a lot of environments in parallel. With Brax, we can easily have, what was it? I think we can do something like 120,000. Yeah. Here we can do 30,000 evaluation per second with Brax. And what we observed is very quickly, when you try to get this kind of scaling on mappability with gradients, the limiting factor becomes actually the training of the actor critic. Because you have 13,000 evaluation that leads you to 30,000 trajectories per second times 200 or 1,000 transition. That's a huge replay buffer. Then you need to go through the entire replay buffer with your actor critic, and it's challenging to actually distribute and scale perfectly. So actually what we observe is no, you just brute forcing the evaluation and using simpler algorithm might be actually more resource efficient or time efficient than actually more complex algorithm. So here, in a sense, the cost is not quite straightforward, and sometimes there are maybe some benefits of doing more evolution and a little bit less model-based optimization. Yeah.
So it's a question for inference time, basically. It seems like the traditional case for this is there's like one trigger to force you to adapt, and then you can run some adaptation mechanism, and then you find the next kind of best static new behavior.
Yes.
And questions about basically continuous adaptation. So first, are there good benchmarks or test cases for how to evaluate how good we are at continuously adapting? And if you guys have methods that might work for that setting as well. And how then, you trade off exploring versus exploitation now in this like behavior finding space.
Good question. I think this is, from my view, an underexplored field. We have just a couple of papers in this direction. One prominent example is in the DARPA challenge that I showed. We have a lot of scenarios where actually during the runtime, so we were doing laps in the deserts of New Mexico, and every 1 minute or two, the situation was changing, like it was a different tire that was exploding and so on. But what we observed is that with our new algorithm, we were able to adapt in less than 200 milliseconds. So in this case, it was actually better to just detect if the situation was changed, clear everything we learned, and just readapt in 200 milliseconds, and we were done. So it's not super smart, but it was very effective. Another thing we did was this kind of reset free, where we always try to predict what would be the consequence of our action. But that was not really putting into question and retriggering training. So I think it's a very interesting lines of research, but we haven't explored that much at the moment. So there's a question.
Yeah, so this is just a question about the descriptors. So just to make sure I understand this, is this a similar paradigm to physics-informed neural networks, where your descriptors are a constraint during training to make the model behave in a certain way, or is that incorrect?
I think it's more just a way to characterize the types of solution you have. So the idea is that usually your fitness or reward function will define the problem that you are solving. But for given problems, there may be different solutions. So for instance, if the problem is to find the exit of this room, which is this door over there, there are a lot of different solutions. I can just go this way, I can go this way, I can go that way, I can step on the table. So there are different types of solutions, all of them solving the task, but differently, and with potentially different performance trade-off, let's say. And this diversity is what we look, because for instance, if there is a tripod with a camera that is an hazard, something like this, I can just use another solution. So it's not in a way to constrain the model to behave in a certain way, just to make sure that we have a catalog of solutions that are all very performing, but all very different from each other.
So I think this might have been asked earlier. I just wanted to make sure I understand it. So when you're exploring the descriptor space, how do you ensure that you get a solution for every part of the descriptor space?
We don't, but the thing is, given that we always start from a solution that is already somewhere in the space, and we then mutate it or perform some variation, there is a high chance that the perturbation will actually explore new cells around. And it's kind of this expanding pattern that just progressively propagate through the descriptor space.
Okay, so there's no prior or anything?
No.
Okay, thank you.
Yep.
Slightly off topic.
Good.
You mentioned exploding plans. How many robots have you destroyed by accident?
How many? Too many. But the good thing is that I build my own robots, so that's not too much of a big deal. So I break one robot and I build another 5 others and so on. But yeah. I had one robot that took fire at some point, but that's another story.
So you did talk about how, and maybe I misunderstood this, but you did talk about how the evolutionary algorithm side of it was often doing the optimization in
Mhm.
certain parts, which is counterintuitive in a sense, rather than the diversity part.
Mhm.
Do you think this, I don't exactly know how to read this in terms of what does this exactly, lead to, or what does this mean? Does this potentially imply certain limitations on how good this can become?
Mhm.
Or does it imply something else? What's my takeaway from this? I guess very interesting.
So can you just
finding.
repeat which parts? What I said make you think that?
Yeah, maybe I misunderstood this,
Mhm.
but you said what you'd actually seen across a bunch of experiments
Yeah.
is that the I guess compared to the evolutionary part mostly contributing to the diversity and the policy gradient contributing to how well something becomes, you actually see that the evolutionary part also sort of
Mhm.
contributes to finding finding quality samples. Is that, I guess that's kind of counterintuitive, at least to me. Does this imply something in terms of how far this can go or something else?
So my interpretation of this is just that at some point, the models that we build in an actor critic start to be a little bit too noisy and too imperfect, or maybe sometimes too conservative, making sure that we always minimize the variance in every different stages of the algorithm, maybe just too conservative to find the right solution, to maybe explore something new, or to just find a small tweak of the same policies that will just change, populate the cell just next door. And conversely, being way more down to earth, more closer to the parameters and directly perturbing the parameters and forming kind of an empirical gradient, so for instance, with evolutionary strategy, is actually way more detached from all those limitations and might be a better way. So my opinion is actually deep reinforcement learning is very good at pushing the algorithm in the right location of the search space, and then we can just have like some more low-level approaches to try to do the final optimization. But what is interesting, both of them seems to contribute in the diversity, because sometimes in order to, when you go very quickly to the optimal solution following the gradient, you actually encounter new solution along the way. But at some point, beasts start to vanish while the evolution maintain its feasibility or its capabilities. So it's not very high at the beginning, not very high at the end either, but it's actually still promoting things even after 1 or 2 million of evaluation. Good.
Well, we have one question from Tom Aloka from the Paris office.
Yeah.
So how fast does your fitness function need to be to use QD methods in practice? How much time should one evaluation take for you to consider QD usable? And perhaps I would extend the question, like, could you share any practical guidelines, or like what are the criteria that we should consider if we want to apply QD methods in practice?
Yeah, this is an excellent question. Indeed, if you're so every time I mention evaluation, I'm saying like millions of evaluations. So if your evaluation are taking just 1 minute, forget about it. So definitely that's the bottleneck. And I would say on the other end, if you have a problem where you can do a lot of evaluation very rapidly and even more in parallel, so namely DRAX, then QD is a very, very good setup for you. But there are a lot of ways where you can actually use model in order to avoid, testing directly. So we have actually, I removed those slides from my presentation, but we have some method for model-based quality diversity, where you actually optimize the output of a neural network, like a world model or a dynamic model, and that works quite well. And so that's typically what we do a lot of time with everything related to proteins and crystal structure. We don't develop the proteins in vitro. That's too long, too slow. What we do is that we use a model, either pre-trained or that we train along the way with the data collected by QD, which tends to, we have a couple of papers that shows that actually the data generated by QD, given that it's diverse and high performing, gives very good training grounds for predictive models. And that usually works quite well. And so in robotics application, we demonstrated a speed up of 20 times. So we can run things directly on the real robot without any simulation, just by learning the dynamics model, a little bit like Dreamer v3 on the system.
Any other question? Cool. Well, thank you very much, Antoine, for this presentation.
Thank you, everyone.